Hello friends, today I start the next part of transition and inner transition element that we start in our last lecture. So first, that is what we studied, that we just go through once again. In our last lecture, we start with a transition series. In that, first of all, we see how many transition series in your periodic table. First, that is your transition element is placed between your S block element and P block element. So transition element is nothing but are nothing but D block element. Means their unpaired electron or their valence electron enter into n-1 d orbital. Now this transition element are placed in periodic table from group 3 to 12 and in a period that is from 4 to 7. So our first transition series in period 4, that is which containing their last electron in this 3D in the 3D orbital, means their last electron enter in 3D subshells. So this is our first transition series. Second means first transition series is start from scandium and end to the element that is zinc. Then second transition series start from yttrium to cadmium. So this is our second transition series. Okay, and third transition series, that is start with lanthanum and end into mercury. And our last transition series, that is in period 7, start from actinide and end with a CN, that is nothing but the our man-made element, that is copernicium. Okay, so as in our last lecture we studied, that is there are 4 series for transition element. 3D series whose characteristics electronic configuration start with the argon as an inert gas, and in 3D electron accommodated from 1 to 10 and 4s, that is 1 to 2. Then our second transition series, that is nothing but 4D series, in which they are starting, that is a krypton is a inert gas element, then 4D, that is 1 to 10 and 5s, that is 0 to 2. Then 5D series, which start with the xenon as an inert gas, then 5D 1 to 10, 6s2. And our 6D series, that is inert gas is radon, 6D 1 to 10 and 7s2. So this is just an introduction part of our transition element. Now next we studied its oxidation state, that is transition element can show variable oxidation state, and this oxidation state is possible due to their, as the 4s and 3d orbital are very they have a very low energy difference, so they can shift the electron. So the in first transition series, your manganese element showing highest oxidation state, means it can show oxidation state that is from +2 to +7. Okay, and the common oxidation state is nothing but +2. Okay, so oxidation state they are showing because they have a very low energy difference in their 4s and 3d orbital, and there is the availability of unpaired electron in 3d subshells. Next, we study the physical property of first transition element. Means in that we study what is the nature of our transition element. So they are generally metallic in nature because they showing the property similar to metal. That is they are hard, lustrous, malleable, ductile. Okay, and in this series some element showing highest melting point. Then we start our next part, that is trend in atomic property of first transition series. In that we have to see atomic and ionic radii. Second one we seen that is ionization enthalpy. Third one is metallic character. Fourth one is magnetic property. Fifth one is a color. Sixth is catalytic property. Seventh is formation of an interstitial compound. And eighth is formation of a alloy. But in this we in our last lecture cover that is atomic and ionic radii, ionization enthalpy and metallic character. We just once again go through these three properties that we studied in our last lecture. So first is atomic and ionic radii. What happens as we move across a transition series, that is from left to right, its nuclear charges increases. But one thing is remember, the last filled electron enter into the penultimate shell, that is our n-1 d subshell. So d orbital are less penetrating or more diffuse. So that's why your d electron offer smaller screening effect. So in this way your effective nuclear charges goes on increasing as the atomic number increases, and this is the reason why your atomic radii decreases gradually across the transition series from left to right. So for atomic and ionic radii, for atomic radii what we conclude, that is atomic radii decreases gradually across a transition series from left to right, and reason for that is the nuclear charges increases by unit at a time from left to right in a period, and your last electron enter into the penultimate subshell. So d orbital in an orbiter are less penetrating or more diffuse. Therefore, d electron offer a smaller screening effect. So your effective nuclear charge will increases from left to right as the atomic number increases. And this is the reason why your atomic radii decreases gradually. Now we see some concept regarding ionic radii. So ion are formed by loss of electrons. Okay. So this can be studied on the basis of two factors. That is, you have to consider element having same oxidation state. This is our first case. Or second case is what? You have to consider various oxidation state of a same element. Now in first case was what we studied, that is as the increase of a nuclear charge there is a gradual decrease in a ionic radii. Means if you compare chromium 2 plus and copper 2 plus, so chromium 2 plus have a higher ionic radii as compared to your copper 2 plus. These elements both are different element but they have a same oxidation state. So your observation is what? As the nuclear charge increases, your ionic radii gradually decreases. Now second factor, that is the oxidation state of a same element with different showing different oxidation state, means the same element showing different oxidation state. So if you compare, that is chromium 2 plus and chromium 3 plus, so what happened? Your chromium 2 plus showing higher ionic radii as compared to your chromium 3 plus. Okay. Now next property that we studied, that is nothing but ionization enthalpy. Ionization enthalpy for the transition element, that is the intermediate between S block element and P block element. Okay, means this suggested that your transition element are less electropositive than element of a group 1 and 2. So depending upon this condition, they can form ionic as well as covalent bond. So one thing is, remember, the lower oxidation state showing compound are ionic in forming ionic compound, while higher oxidation state forming covalent compound. Now we see the ionization enthalpy, that is first ionization enthalpy, second ionization enthalpy, third ionization enthalpy of the transition series. Okay, so in that, if you observe your, that is the element of a third transition series which possesses 4f orbital, field 4f orbitals, so that have a poor shielding effect, and due to its peculiar diffuse shape, what happens? There is a greater amount of energy required to ionize the element of a third transition series. So your observation is what? The ionization enthalpy of a third transition series are much higher than that of your first transition series. Now next we see, that is metallic character. So in metallic character also, what we learn, that is they are showing some typical metallic property, and they have some, that is your solid properties, solid substance properties, that is nothing but they showing cubic close packing, then body center cubic, then hexagonal close packing, such type of form. And now we start our remaining property, that in this lecture we try to cover the remaining property, that is magnetic property, then color, catalytic property, formation of an interstitial compound, formation of alloy, that we see one by one. So now we start with a magnetic property. Now first of all, why they are showing magnetic property? This is our question. So this transition element, means the compound of a transition metal, exhibit magnetic property, and the reason behind that, they have a unpaired electron present in their atom or ion. So this compound, the compound of this transition element showing magnetic property due to the presence of unpaired electron present in their atom or ion. Now when you apply magnetic field, the substance are whenever attracted toward the applied magnetic field, then it is paramagnetic, while the one which are repelled are called diamagnetic. So next substance, that is are strongly attracted, and these are called ferromagnetic. So your magnetic substance divided into three types, that is nothing but paramagnetic, diamagnetic and ferromagnetic. So paramagnetic means what? They are attracted toward the applied magnetic field. Diamagnetic means what? they are repel in applied magnetic field. And ferromagnetic means what? They are strongly attracted toward the applied magnetic field. So in this transition series, which element act as a ferromagnetic? So iron, cobalt and nickel are ferromagnetic in nature. in nature. So now when magnetic field is applied externally, so what happen? The compound of this transition element which containing unpaired electron, okay, so they are aligned in the direction of a applied magnetic field. Means when you keep any compound of this transition element in a external magnetic field, so the unpaired electron present in that transition metal align in the direction of a applied magnetic field. So this was enhance their magnetic susceptibility. So the metal can be magnetized as they acquire a permanent moment. So now, as in our previous slide, what we summarize, that is magnetic field is due to the presence of unpaired electron. Okay, and your magnetic substance divided into three types, that is nothing but paramagnetic, diamagnetic, ferromagnetic. Okay, iron, nickel, cobalt can act as a ferromagnetic substance. Paramagnetic are attracted toward the applied magnetic field, diamagnetic are repel, and ferromagnetic are strongly attracted. Okay, and now when you apply the magnetic field, what happens? Your unpaired electron which is present in a transition metal or ion are aligned in the direction of a magnetic field. So next what happens? So your each unpaired electron give rise to a small magnetic field. Means they itself create a new magnetic field, that is a small magnetic field, and that is due to its spin angular momentum and orbital angular momentum. As you studied in physics also, what is spin angular momentum? That is due to the electron revolve around itself, so that create a spin angular momentum. And what is orbital angular momentum? The electron when revolve around the orbit, that create a orbital angular momentum. But now what happened? For the first row of a transition element, the contribution from the orbital angular momentum is quench. Means there are the two reasons due to which there is a small magnetic field is created by this unpaired electron. First is due to the spin angular momentum, and second one is a orbital angular momentum. But in your first row of a transition element, the contribution due to the orbital angular momentum is quench and you can be neglected. So the magnetic field is due to the spin only formula, and that is given by mu is equal to square root of n into n plus 2. Bm is nothing but Bohr magneton. So your n is what? Number of unpaired electron. Mu is what? Magnetic moment expressed in a Bohr magneton. So now if you know, as you know, n is the number of unpaired electron. If n is equal to 1 here, okay. So now what is your magnetic moment for single unpaired electron? Mu is equal to square root of 1 into 1 plus 2, that is nothing but square root of 3. So that come as a 1.73 Bohr magneton. So in your exam also they may ask you if your magnetic moment is 1.73 Bohr magneton. Okay, so what is your number of unpaired electron in that element? So you have to calculate that. As from the magnetic moment measurement of the metal complexes of a first row transition series, the number of unpaired electron can be calculated. Means with help of this spin only formula, you can calculate number of unpaired electron in your first row of a transition element. Okay. So one thing is always remember, that is magnetic moment is directly related to the number of a unpaired electron. Means mu is directly connected with the number of unpaired electrons. Now this magnetic moment are determined experimentally. So you can find out the magnetic moment experimentally when your central metal ion is in a solution or in a solid state and where your central metal ion is hydrated or bound to the ligand. Means your transition element in a solution or in a solid state, but that transition element should be hydrated or bound to the nucleus. Okay, but when you find out the magnetic moment experimentally, so there is some change. That is the difference between the calculated and the observed value of your magnetic moment. Okay, so your magnetic moment calculated value and observed value both are somewhat different. There is a not marginal difference, but there is a small difference in both the values. So the calculated and the observed magnetic moment of the cation of 3D series as shown in this table. Now see the scandium, which is in a 3+ oxidation state. Here it's in 3D orbital there is a 0 electron. Means number of unpaired electron will be 0. And calculated value of the magnetic moment will be 0 for this, and experimental value also 0. Now see the next element, that is titanium in 3+ form. That is 3D1 outer electronic configuration. Now number of unpaired electron in this case is 1. But the calculated value of magnetic momentum will be 1.73. But there is a very slight difference in experimental value. That is experimental value is 1.75. Now next is vanadium. So vanadium in 3+ oxidation state, outer electronic configuration will be 3D2. So number of unpaired electron will be 2. The calculated value of a magnetic momentum will be 2.84 and experimental value will be 2.76. Now next is chromium in 3+ oxidation state. So in 3+ oxidation state it have a 3D3. So 3 unpaired electron. So calculated value for magnetic momentum will be 3.87 and experimental value will be 3.86. Next is chromium 2+. So whenever it is in a chromium 2+, so at that time the outer electronic configuration 3D4. So there are 4 unpaired electron. So calculated value of magnetic momentum will be 4.90 and experimental value will be 4.80. For manganese in 2+ oxidation state, 3D5 is its outer electronic configuration. So number of unpaired electron, that is 5. So calculated value of magnetic momentum will be 5.92 and experimental value will be 5.96. If you observe in your transition series, there are maximum unpaired electron, that is nothing but 5 unpaired electron. Okay, so that's why this is your maximum magnetic moment value. Okay, so similarly whenever iron once again showing 4 as unpaired electron, so calculated value is same as your chromium 2+, that is nothing but 4.90 and its experimental value between 5.3 to 5.5. Similarly for cobalt, when it's showing +3, has a cobalt in +2 oxidation state, so outer electronic configuration will be 3d7, so number of unpaired electron will be 3, so calculated value will be 3.87, and experimental value will be ranging between 4.4 to 5.5. Means one thing is, remember, from magnetic momentum value you can calculate the number of unpaired electron in your elements, in your ions. Okay. Now in second and transition series, what happened? Your magnetic momentum is due to the two factor, that is spin angular momentum and orbital angular momentum. But in your first transition series, orbital angular momentum will be negligible, or you can neglect it, okay, because it is quench. But in a second and third transition series, the orbital angular momentum is significant. So what happened? Therefore the previous formula, that is the spin only formula, is not useful for calculating magnetic momentum of second and third transition series. So more complicated equation have to be employed to determine magnetic moments. Okay, so in magnetic property, what we study, first of all, magnetic property is due to the unpaired electron present in your element, and your magnetic substances are divided into three types, that is nothing but paramagnetic, diamagnetic, ferromagnetic. Then next is what? That is paramagnetic are attracted towards the magnetic field, diamagnetic are repelled, and ferromagnetic are strongly attracted. So which element of a transition series are ferromagnetic? Iron, cobalt and nickel. So what happens when you apply magnetic field? Your unpaired electron will align in the direction of a magnetic field. So what happened? Due to the unpaired electron have a magnet apply the small magnetic field due to its spin magnet angular momentum and orbital angular momentum. But in your first transition series, only spin angular momentum can be considered, and you can be calculate magnetic moment by using the formula mu is equal to square root of n into n plus 1, Bohr magneton. N is the number of unpaired electron and mu is the magnetic moment, which express in Bohr magneton. Okay, so from this formula you can calculate number of unpaired electron in your first transition element series. But this method you can't apply for second and transition series, and the reason for that is for second and transition series the magnetic moment is due to the spin as well as orbital angular momentum, and that is the reason the spin only formula you can not be used for calculating the magnetic momentum of second and third transition series. So for that, more complicated equation have been employed to determine the magnetic moments. So in this way, and one more thing, that is magnetic moment are found to be temperature dependent properties. So in this way we completed our magnetic momentum property. Now we start with the colors. So color. So if you observe, means whenever your substance is appear to be color. So why it appear to be color? Because it is absorb a portion of a visible light. As you seen in this diagram, that is, this is color. Okay, so when your substance absorb color absorb light in a visible region, so at that time your substance will be appear to be colored in nature. Okay, so color basically depend on what? So color depend upon the wavelength of absorption in visible region of electromagnetic radiation. So when you see any color to the substance, this is due to the absorb the light in a visible region. Okay, and the color is totally depend upon the wavelength of absorption in a visible region of electromagnetic radiation. Okay, now as you know, the transition element are forming ionic and covalent compound. Okay, so that's why the ionic and covalent compound formed by the transition element are colored in nature. Okay, next is what? The transition element contain unpaired electron in their d orbital. As you know, the in your transition series, the unpaired electron present in a d orbital, d subshell. So when the atom are free or isolated, the 5d orbital are degenerated or have a same energy. Okay, means what? As you know, your transition element are forming ionic and covalent compound. Okay, so they are colored in nature. So why they are colored? Because they contain unpaired electron in their d orbital. At the same time, when transition atom are free or isolated, so what happen? They have a 5d orbital which are degenerated or have a same energy. Degenerated means what? They are equal in energy. Okay, so they are degenerated means they are nothing but all d orbital are appearing like a same. Okay, so degenerated means similar in nature. Next what? When in a complexes form, this transition metal ion is surrounded by your solvent molecule or ligand. So what happen? This 5d orbital which is degenerated or in a same energy are now no longer having same energy. Means in a complexes form, your metal ion is surrounded by solvent molecule or ligand. So what happened? This solvent molecule or ligand affect the energy of a d orbital and their energy are no longer the same. So now as the principal quantum number of d orbital is same, the amount of energy required for transition of an electron from one d orbital to another is quite small. Okay, so the very small amount of energy is required for transition. So that's why they absorb the radiation from a visible region. Okay, and the remaining light is transmitted. The observed color of the compound corresponding to the means complementary color to the light absorbed. Means if red light is absorbed, so the transmitted light contain excess of other color in the spectrum. So in particularly blue. So the compound appear to be blue. So what is our summarized point for this color? So as you know, your transition element forming ionic or covalent compound which are colored in nature, and this is possible due to they have a unpaired electron in their d orbital. Now as the atom or an ion in a free state, they have all d orbital having are degenerated or have a same energy. But in a complex form, what happen? This metal ion is surrounded by solvent or ligand molecule. So the surrounding molecule affect the energy of your d orbital and their energy are no longer same. So as you know, this d orbital have a same principal quantum number. So what happened? The very small amount of energy is required for transition of an electron from one d orbital to another. Okay, and that small amount of energy that they taken from visible region. Okay, now which color they appeared? So the light is transmitted and the observed color of the compound correspond to the complementary color of a light absorbed. Means if they absorb the red color light, so what happen? Transmitted light contain excess of other spectrum color in the spectrum. So in particularly blue. So compare compound appear to be blue in nature. Okay. So the ion having no unpaired electron are basically colorless. So the compound which doesn't containing any unpaired electron, so they are a colorless in nature. Now let's see how the color of a transition metal ion depend upon ligand and the geometry of the complexes formed by the ligand metal ion. Means how your color of the transition metal depend upon your ligand and geometry of the complex formed by the metal ion. Now see, when cobalt chloride is dissolved in a water, it forms pink solution of the complex. Okay, so when cobalt chloride dissolve in a water, it form a pink chloride solution. Okay, and the cobalt hexaqua complex which has a octahedral geometry. But when the solution is treated with a concentrated hydrochloric acid, means first of all you take a cobalt chloride and you dissolve in a water. So your observation is what? Pink solution is appeared, and as the hexaqua complex of cobalt is formed which has a octahedral geometry. Color is pink, geometry is octahedral. But when this solution is treated with concentrated hydrochloric acid, so what happened? It turned deep blue. Means the change is due to the formation of another complex, that is cobalt chloride, which has a tetrahedral structure. Means when it has an octahedral structure, at that time solution will be pink in color, and when it has a tetrahedral structure, so the color of the solution will be turned into deep blue. Now the color of the transition metal ion are related to the following factor. So first factor is what? Presence of unpaired d electron. Second is what? There is a dd transition. Third is what? Nature of a ligand attached to the metal ion. And fourth is its geometry of the complex formed by the metal ion. Okay, so when you summarize for color, so these are the factor which affect the transition metal ion color. So first factor is what? Presence of an unpaired d electron. Second is what? dd transition. Third is what? Nature of a ligand attached to the metal ion. And fourth is what? Geometry of the complex formed by the metal ion. The last two as we seen by taking the example of cobalt chloride. So cobalt chloride dissolve in a water, so it is pink in a color because it has an octahedral geometrical complex. Similarly, when this solution once again treated with a concentrated hydrochloric acid, so at that time it is deep blue color, and this is due to the formation of a tetrahedral structure, that is nothing but your cobalt chloride. Okay, now see the color of a 3D transition metal ion as shown in a figure. Now if you seen in this table, what we do, that is ion, then outer electronic configuration, number of unpaired electron and color. Now see, when you have number of unpaired electron 0, because the color of a transition element is depend upon the number of unpaired electron. So see, whenever you have number of electron in this table 0 0 0, at that time your compound appear to be colorless in nature. Okay. Similarly, when you have unpaired electron 1, so whenever it is titanium, so at that time it is purple in color. Okay, similarly one more number of unpaired electron when 1 for copper, so at that time it is blue in color. Okay, next is what? When you have number of unpaired electron, that is 2. So the vanadium 3 plus oxidation state, its color will be green. Similarly, for nickel in +2 oxidation state, number of electron will be same as your vanadium. So color will be same as green. Now for chromium in 3 plus, its number of unpaired electron will be 3. So at that time it appear will be, its color will be violet in color. Okay. Next 3 unpaired electron for cobalt 2 plus. So that appear to be pink in color. Okay. Next is for manganese in +2 oxidation state. Okay. Whose number of unpaired electron will be 5 and its color will be light pink. And for manganese 3 plus, number of unpaired electron will be 4. It appear will be violet in color. And iron in +2 oxidation state, number of unpaired electron will be 4. It appear to be pale green. Okay. Iron in +3 oxidation state, whose number of unpaired electron will be 5 and it appear to be yellow. So see, when you go through this table, so at that time you must know the color. Okay, the color is depend upon the number of unpaired electron. In some cases, if number of unpaired electron is same, that is 1 1, so at that time 2 2, so at that time color will be same. But in some cases there may be a slight changes, so you must know what is the color of your compound when it is present in a titanium +3. So you must know the number of unpaired electron will be 1. So at that time what is the color of that compound? Okay. Similarly they may ask you for copper. So copper 2 plus. So number of unpaired electron will be 1. So at that time it appear to be blue. And for number of unpaired electron 0, then the compound appear to be colorless in nature. Okay. As you can see that the color of the transition element is depend upon the 4 factor. That is, first is the number of unpaired electron, second one is the DD transition, third one is the type of ligand which is attached to that metal ion, fourth one is the geometry of your ligand, means geometry of that complex. So when you study color, so at that time you must know what is the point, that is you must know what is the requirement, that is unpaired electron is required, DD transition is required, and why DD transition is possible, that also ask in your exam. Okay. Then the last the remaining two, that is the nature of a ligand or the geometry of your complex, that can be explained by considering the example as we discussed in our last PPT. Okay. Now next is our catalytic property. So first of all, before starting with the catalytic property, everybody must know what is the action of a catalyst or what is the meaning of a catalyst. So catalyst means what? That is, they doesn't form, they just increase the rate of reaction. Okay, means as you take what is the amount in the starting of the reaction, that much of amount must be written at the end of your reaction. Means they speed up the reaction, but they doesn't take part in any reactions. Okay, the transition metal and their compound exhibit good catalytic property. Okay, so they have proven to be good homogeneous and heterogeneous catalyst. Now what is the meaning of homogeneous and heterogeneous catalyst? Means homogeneous means what? Your catalyst are in the same phase as that of your reactant. And heterogeneous catalyst means what? Your catalyst are in a different phase than that of your reactant. Means if reactant are in a solid phase, your catalyst also in a solid phase, then it is a homogeneous catalyst. But if your catalyst is in a solid phase and reactant in a gaseous phase, then it is a heterogeneous catalyst. Okay. Now next, partially because of their ability to participate in different oxidation reduction state of a catalytic reaction. So this step involve change in oxidation state of these metal ions. Now which compound can be taken as a catalyst? So compound of an iron, cobalt, nickel, palladium, platinum, chromium, etc. are used as a catalyst in number of a reaction. So their compound enhance the rate of a chemical reaction. Means transition metal and their compound have a good catalytic property. They can be used as a good homogeneous and heterogeneous catalyst, and at the same time they have a ability to participate in a different oxidation reduction step of a catalytic reaction. Okay, so compound of iron, cobalt, nickel, palladium, platinum, chromium can be used as a catalyst in number of a reaction. In homogeneous catalysis reaction, the metal ion participate by forming unstable intermediate. Now for homogeneous catalysis, what happen? The metal ion participate by forming an unstable intermediate ion in that. And in heterogeneous reaction, catalysis reaction, what happen? The metal provide a surface for reactant to react. Means whenever you take homogeneous catalysis reaction, so at that time your metal ion participate by forming unstable intermediate, and whenever you studied any heterogeneous catalysis reaction, at that time your metal provide a surface for a reactant to react. Now we see some example of a catalyst means transition element where we are using as a catalyst. So first example is MnO2. Now this is a manganese oxide, okay, which act as a catalyst for decomposition of KClO3, potassium chlorate. Now next is what? In Haber's process of ammonia, where we are using molybdenum and iron as a catalyst. Third one is cobalt-thorium alloy we are using in Fischer-Tropsch process in synthesis of gasoline. Okay, then finely divided nickel. This is formed by reduction of a heated oxide in hydrogen, is an extremely efficient catalyst in hydrogenation of ethene to ethane. Now see, when you have a ethene as a double bond and you have to reduce into that ethane part, so at that time we are using finely divided nickel. Okay, so reaction is that is ethene plus hydrogen, and you required 140 degree as a temperature, and catalyst is your finely divided nickel. You get a ethane from that. Commercially, hydrogenation with a nickel as a catalyst is used to convert your inedible oil into solid fat for production of a margarine. Okay, so now see in this example, in your exam also they may ask you some example for catalytic property. So at that time you must at least remember this at least 4. So that is easy one. MnO2 act as a catalyst for decomposition of KClO3. Similarly, in manufacture of ammonia by Haber's process, you require molybdenum and iron as a catalyst. Cobalt and thorium alloy required for synthesis of gasoline. Run in nickel in reduction of your ethane to ethane. Okay, so in this way, you can convert your inedible oil into solid oil or solid fat for production of a margarine. Now next example is what? That is in contact process. Okay, means in production of your sulfuric acid, where your sulfur dioxide get converted into sulfur trioxide with the help of a catalyst, that is a platinized asbestos. Now next is carbon dioxide and hydrogen are formed by reaction of the carbon monoxide and steam at about 500 degrees Celsius with an iron chromium as a catalyst. Okay, so in this case, in this example, we produce hydrogen, okay, from water gas. So this is nothing but our Bosch process for production of a hydrogen gas. Okay, so these are some example where we are using transition element which showing the catalytic property. So 6 example are there. So catalyst is now known to you. What is the catalytic property of your transition element? Now we start with our next property, that is formation of a interstitial compound. Okay, now in formation of an interstitial compound, what is the meaning of interstitial compound? First of all, so when small atom like hydrogen, carbon or nitrogen are trapped in a interstitial space within the crystal lattice, the compound formed are called interstitial compound. See, whenever a small atom, that may be your hydrogen, that may be your carbon, or that may be your nitrogen, that are trapped in an interstitial space within the crystal lattice of this compound, then the compound form are called interstitial compounds. Okay, sometimes sulfide means beside hydrogen, carbon and nitrogen, sulfides or oxides may also get trapped in the crystal lattice of transition element. Now the example for interstitial compound is steel and cast iron. Okay, are example of a interstitial compound of carbon and iron. Means in this case iron is your transition element. In that crystal lattice carbon is trapped. So due to the presence of carbon, what happen? The malleability and ductility of iron is reduced while its tenacity will increases. So this enhance the property of your metal, that is a transition element. So in steel and cast iron, that is the interstitial compound of carbon and iron, and due to the carbon, the malleability and ductility of iron is reduced and its tenacity will increase. Now some properties of a interstitial compound. So what are the properties of interstitial compound? So they are a hard and good conductor of heat and electricity. Second property is what? Their chemical property are similar to their parent metal. Third one is their melting point are higher than pure metal. Okay. Fourth one, their densities are less than the parent metal. And the metallic carbide are chemically inert and extremely hard as a diamond. And hydride of this transition metal are powerful reducing agent. So in exam, they may ask you the properties of an interstitial compound. So at that time, what you have to write? They are a hard and good conductor of heat and electricity. Their chemical property are similar to their parent metal. Their melting point are higher than the pure metal. Their density are less than the parent metal. And the metallic carbides are chemically inert and extremely hard as a diamond. And hydride of a transition metal are used as a powerful reducing agent. Now we formation of alloy. That is our next property, formation of alloy. So what is first of all alloy? Okay, so transition metal form alloy where atoms of one metal are distributed randomly in a lattice of another metal. So this metal will having similar radii and similar property, so they readily form alloy. So for alloy, your two metal are distributed randomly, okay, and the metal with a small similar radii and similar property readily form alloys. So alloy are classified into ferrous and non-ferrous alloy. So first of all, what is ferrous alloy, and then we see what is non-ferrous alloy. So ferrous alloy means what? Ferrous alloy have an atom of other element distributed randomly in atom of iron. Means one atom is fixed, that is nothing but your iron. In that you add another element, okay. But non-ferrous alloy means what? They are a mixing atom of a transition metal other than iron. Means in that both the atom may be different than iron, okay. So in ferrous alloy, the percentage of iron is more. So that's why you called him the ferrous alloy. So example is what? Nickel steel, chromium steel, stainless steel. So all steel have 2% carbon. And for non-ferrous alloy, what is your example? That is nothing but brass, which is an alloy of a copper and a zinc, okay. So in alloy, what you have to know, that is your atom of a one metal are distributed randomly in lattice of another metal, okay. And what is the requirement for that? This metal with a similar radii and similar property readily form alloy. So you have a two types of alloy, ferrous and non-ferrous. In ferrous, one of the atom, that is iron, and other is the other element. And for non-ferrous non-ferrous alloy, both the atom of different transition metal other than iron. Next is ferrous and non-ferrous alloy are of a industrial importance. Okay. Next, uses of alloy. In uses of alloy, first is bronze, an alloy of a copper and tin, is a tough, strong, corrosion resistance, and it is used for making statues, medals and trophies. Okay, so we are now see the what is the uses of alloy. So first is a bronze, which is the alloy of a copper and tin. That is tough, strong, corrosion resistance, and it is used for making statues, medals and trophies. Next is a cupronickel, that is the alloy of a copper and nickel. These are the example of non-ferrous alloy only, because in this there is a no ferrous ion, no ferrous atom. So nickel is used for making machinery part of a marine ship, boats. For example, marine condenser tube. Next one is a stainless steel. Now this is known as it is used in construction of a outer fuselage of a ultra high speed aircraft. Okay, next, that is nichrome, an alloy of a nickel and chromium in the ratio of 80:20, and it is specifically used for gas turbine engines. Okay, turbine engines. Next one is titanium alloy. Okay, which withstands, means stress up to high temperature, and are used for ultra high speed flight, fireproof, bulkhead and exhaust shrouds. So in this way, in your exam they ask you the uses of alloy. So bronze, cupronickel, stainless steel, nichrome and titanium alloy. Okay, in this way we complete all the atomic property of first transition series. Thank you.